Welcome to this educational video on metals in European soils and phytomanagement, a sustainable remediation approach, by Eleni Papazoglou and Berian Elbison. Soil is a crucial natural resource that sustains systems vital for both rural and urban populations. However, soil pollution is a growing concern, affecting human health and the environment, as well as reducing the ability of soils to provide services. Soil pollution is defined as the presence of a chemical or substance in the soil where it should not be, or at concentrations higher than natural levels, leading to harmful effects on organisms that were not meant to be exposed to them. Worldwide, more than 10 million major sites are polluted. In the past decade, the European Commission's Joint Research Centre and the European Environment Information and Observation Network has conducted a comprehensive survey across 39 European countries. Their findings revealed that approximately 2.5 million sites are potentially contaminated, with 37.3% of these sites being affected by contamination with metals and metalloids. At the moment, there is no EU-wide spatially specific dataset available on the location of polluted sites, their pollution status, nor their remediation progress. However, within the framework of the GOLD project, a European Union Horizon 2020 programme, efforts are being made to increase our understanding of the types of polluted lands that exists, and to evaluate their potential for integrating soil remediation with biomass production for the generation of biofuel. Soil pollution can be local, from a point source, or diffuse, through different compartments in the environment. Let's focus on point source pollution. Point source pollution refers to pollution that originates from a single identifiable source, such as industrial facilities, landfills, or quarries. Understanding the spatial extent and characteristics of such pollution is critical for effective remediation strategies. In this table, we can see the findings of the GOLD project, which highlight the distribution of potentially polluted sites across Europe. The largest categories of potentially polluted sites were identified using OpenStreetMap, and were found to be military areas, industrial sites and brownfields, quarries and landfills. Across the EU27 and the UK, potentially polluted sites that have land cover suitable for phytoremediation, with less than 40% of the area being impervious, comprise a total area of just over 2 million hectares. This area represents approximately 0.5% of the total surface area of these countries. France, Germany, Spain and the UK have the largest total areas of all types of potentially polluted sites, each exceeding 150,000 hectares. Let's move on to diffuse pollution. Diffuse pollution refers to pollution that originates from widespread and dispersed activities rather than a single identifiable source. Common examples include acid rain, the application of pesticides, and urban runoff. Unlike point source pollution, this type of pollution is more difficult to trace and manage due to its diffuse nature. To understand the broader impacts and management difficulties of diffuse pollution, let's explore the main factors contributing to its complexity. Firstly, there is a lack of a discrete source. The widespread nature of diffuse pollution makes it challenging to identify and address a single source of pollution. Secondly, there is also a lack of harmonised risk detection at the EU level. There is currently no unified approach at the EU level to assess the risks of diffuse pollution. Soil screening values for pollutants vary significantly across member states, complicating cross-border management. And a third factor is that the process of pollutant accumulation is slow. diffuse pollution is characterised by a gradual accumulation of pollutants over time. Pollution levels tend to be moderate, and across the EU, most soil screening values are not designed to target these subtle, steady increases. To assess the impact of diffuse pollution, models have been developed to evaluate whether the concentration of specific metals such as cadmium, zinc, lead and copper exceeds critical limits for key environmental and public health factors, including food quality, ecosystem health and drinking water safety. Critical concentrations of metals in soils vary widely, depending on specific soil properties, including the pH, soil organic carbon content and soil texture. These factors influence the bioavailability and mobility of metals in the soil. Additionally, the critical thresholds depend on the intended endpoint of monitoring, such as whether it is for ensuring food safety, protecting ecosystem health, or maintaining drinking water quality. Let's look at some of the sources of pollution with metals and metalloids. Anthropogenic activities are the primary cause of soil pollution with metals and metalloids, contributing far more pollutants than natural processes like volcanic eruptions and mineral weathering, and driving global soil degradation. The main anthropogenic sources of environmental pollution with metals or metalloids are industrial activities, irrigation with contaminated water, combustion of fossil fuels, agrochemicals, mining and smelting activities, and waste disposal. Let's move on to some of the effects of such pollution. In contrast to organic pollutants, metals and metalloids are non-degradable. Once in the soil, they can persist for hundreds of years. They lead to groundwater pollution as they are leachable, and can also affect freshwater and marine environments through erosion by wind and water. These elements are highly toxic to humans and animals, often leading to chronic or severe diseases like cancer, neurological disorders, cardiovascular and renal diseases, as well as bone and developmental disorders. Pollution of soil and water also means that levels of metals in foods can be dangerous. In plants, abnormal concentrations of metals such as zinc, nickel, cobalt and copper can disrupt essential physiological processes, including photosynthesis, enzyme activity and nutrient absorption, resulting in stunted growth and reduced crop yields. High concentrations of metals or metalloids can also affect and alter the native microbial communities in the soil, ultimately destroying its biochemical properties and further exacerbating environmental degradation. Their elevated concentrations in the environment also leads to severe degradation of ecosystem processes, ultimately resulting in the loss of ecosystem services. Therefore, polluted land is unsuitable for food or feed production, but can be utilised for cultivating non-food industrial crops. This approach frees up valuable agricultural land, which is a crucial indicator of economic growth. The remediation processes used for clean-up of sites polluted with metals and metalloids may be physical, chemical, or biological, or even a combination of these. The physical methods of soil reclamation include excavation and disposal in landfill and soil surface replacement, which substitutes polluted soil with contaminant-free soil. Both these methods can be applied to soils that are heavily polluted, shallow and within a limited area. Soil isolation, a prevalent and economically viable physical strategy which involves separating contaminated soil from uncontaminated areas. Thermal desorption processes, which can be used for volatile pollutants, with the resulting vapours being captured by gas collection systems. And electrokinetics, which works by applying a low electrical current to the polluted surface in order to concentrate the metals present on electrodes. The most important chemical remediation methods are vitrification, which heats metal-contaminated soil at high temperatures to improve metal immobilization; soil washing, which uses solvents and mechanical methods to remove pollutants and is suitable for surface soil with high concentrations of pollutants; and soil solidification and stabilization, which is achieved by adding binding agents such as cement or lime, which then limits the migration and diffusion of pollutants. Whilst physicochemical methods for soil remediation are often effective, they are typically expensive and can lead to deterioration of the soil ecosystem. Consequently, there has been growing interest in developing environmentally friendly biological technologies for more sustainable and economical soil remediation. Among biological techniques, bioremediation is a non-destructive and cost-efficient technology that uses the capacity of microorganisms to degrade organic pollutants. However, it is not used for inorganic pollution, because a critical limitation of bioremediation at metal-contaminated sites is that metals themselves cannot be biodegraded. While microorganisms can certainly transform metals from one oxidation state or organic complex to another, they cannot actually remove them from contaminated soil. In contrast, plants often demonstrate higher metal tolerance than microorganisms and can be used in phytoremediation. Most importantly, plants can literally extract metals from contaminated soil and may even immobilize them through various mechanisms, such as sorption by roots, complexation, or metal reduction in the rhizosphere. Phytoremediation is a cost-effective and environmentally friendly set of technologies which will be presented in the following slides. Phytoremediation is a set of technologies that uses green plants to remove pollutants from the environment or to render them harmless. There are two main strategies for metal phytoremediation: phytoextraction and phytostabilization. In phytoextraction, plants remove the pollutants from the soil and concentrate them into their harvestable parts. And in phytostabilization, plants reduce the mobility and bioavailability in pollutants in soil by absorbing them in the roots or binding them within their root zone. Another approach in phytoremediation is phytomanagement, which involves pairing phytoremediation with sustainable and profitable site management options. This approach uses plant species that produce marketable biomass, providing landowners, land managers and stakeholders with economic revenue. The harvested biomass can be used as feedstock for bioenergy purposes, as well as for a wide range of bioproducts with different industrial applications. If we cultivate polluted sites for bioenergy purposes, the biomass produced can be converted to biofuel via various pathways. These include anaerobic digestion, which produces biogas; lignocellulose pretreatment of the biomass, which releases fermentable sugars. These can be converted into bioethanol, bio-oil, or caffeic acid, all contributing to biofuel production. Pyrolysis, which yields biochar, a carbon-rich product; and fast pyrolysis, which produces bio-oil, and finally biodiesel. Other potential industrial uses of biomass produced on polluted sites includes the production of thin films, bioplastics, biochemicals, pulp and paper, biofabrics, biopolymers, construction materials, and insulation panels. Industrial crops suitable for phytomanagement should have the following characteristics. They should be tolerant to soil pollutants. If being used for phytoextraction purposes, they must have the ability to take up and accumulate pollutants in their aerial biomass. Note that in this case, the biomass produced contains high levels of pollutants and must be handled appropriately. Whereas if crop plants are used for phytostabilization, they must have the ability to stabilise pollutants in soil fractions. In this case, the contaminants remain in the soil, resulting in clean biomass. Plants should be high-yielding, fast-growing, and have a widespread, robust root system. They should have low production costs, requiring minimal water and fertilisers, for example, and be easy to harvest. They should be non-consumable by humans and animals, yet can be cultivated on contaminated land while still achieving satisfactory yields and ensuring a reasonable net profit. Now we will examine several examples of biomass crops that have potential for use in phytomanagement. These have been categorised into annual herbaceous, perennial herbaceous and woody species. Let's start with the annual herbaceous crops. Promising examples of these are industrial hemp for cadmium, copper, lead, zinc, chromium, nickel and mercury. Then we have flax, which is good for cadmium, nickel, lead and antimony. Kenaf for cadmium, copper, chromium and mercury. And sorghum, which is useful against cadmium, zinc, lead, nickel, arsenic and antimony. From the perennial herbaceous crops, promising ones are miscanthus for zinc, lead, cadmium, arsenic, chromium, nickel and copper. Switchgrass for cadmium, zinc, lead and chromium. Giant reed for cadmium, nickel, lead, arsenic, chromium and zinc. And cardoon for cadmium, arsenic and nickel. From the woody species, promising crops are willow for cadmium, zinc, lead, nickel and copper. Black locust for cadmium, lead, mercury, arsenic, nickel and copper. Poplar for cadmium and zinc. And eucalyptus for cadmium, mercury and lead. However, phytomanagement as a method for addressing soil pollution has several limitations that must be considered for its successful application. Firstly, there is the slow growth rate of metal accumulating plant species. This means this is an extremely slow technique. The bioavailability of heavy metals in soil is generally low, leading to slow uptake. Remediation is also limited to the depth of the plant rhizosphere. Slow growth also means a slow production of biomass. Therefore, large areas of land are often required to produce sufficient plant biomass for effective remediation to take place. High concentrations of pollutants can actually be toxic to plants, causing stunted growth, reduced biomass, or even death. While phytomanagement can reduce the concentration of pollutants, it does not always completely eliminate them, leaving residual pollution behind. Nevertheless, even if the crops used do not bioaccumulate heavy metals and metalloids in their biomass for the mitigation of soil pollution, phytomanagement can still serve to stabilise pollution by preventing the spread of pollutants to the air and reducing their leaching into water sources. Thank you for watching. Please visit our website and social media to find out more about our project and our partners shown here.